Hello friends, welcome to the concept of biasing and stabilization in bipolar junction transistor. So what we will learn in this video is, we will learn what we mean by biasing, what is the necessity of biasing and what are the different techniques in order to do the carry out the biasing of the transistor as well as the stabilization. So first of all we will see what is the definition of biasing. Biasing is nothing but it's a process of applying external voltage to the transistor circuit. Applying external supply to the transistor circuit so that it works properly. So we know that transistor has three terminals. So the transistor works in three different regions of operation, namely active region, saturation region and cutoff region. So most of the applications we find in active region. Active region, saturation region, region of operation for BJT. So BJT can be biased so that it can be operated in active region, saturation region, cutoff region. Many of the applications, most of the applications we find in active region. So for the transistor to work in active region, it has to be biased properly. So for the transistor to be operated in active region, the input side, I call the input side. See, this is base, emitter and collector. Okay. So input side is base emitter junction. This is the side where we actually give the input. And over here we take the output. So here we call it as output. So input side should be forward biased. Input side should be forward biased and output side should be reverse biased. This is an essential point in order to drive the BJT into active region. Fine. So in order to do this, we will use power supplies, DC power supply. Now we know that the power at the output side of the transistor is more as compared to the power at the input side. How is this done? So this is done due to the DC source whatever we are giving. So this process is nothing but biasing. We have various techniques in order to carry out biasing for the transistor. Basically we have 5 types of biasing techniques, namely fixed bias, biasing techniques in BJT, biasing methods in BJT. So basically we have 5 different methods in order to bias the BJT. So first one being the fixed bias. Then we have emitter feedback bias. Friends, here FB means feedback. Emitter feedback bias. Third one we have collector feedback bias. Collector feedback bias. Fixed bias, emitter feedback bias, collector feedback bias, and next one is the combination of these two things. Emitter collector feedback bias. Emitter collector feedback. Emitter collector feedback bias. And last one is voltage divider bias. Voltage divider bias, which is also named as self bias. Which is also called as self bias. So these are the various techniques in order to bias the transistor so that it forward biases the input side or base emitter junction junction. Along with biasing, we have to have stabilization. Once we set the biasing, we are setting the base current, collector current and VCE. So we should see that this collector current is constant throughout the operation. But this doesn't happen. We know that various factors are there due to which the collector current varies, changes due to temperature, due to change in beta, due to change in VBE, right? But this IC variation is not desirable. Hence, we have to compensate for this IC. So, this is called as stabilization. We have to make the circuit stable. We have to make the collector current stable in the circuit. The process of making collector current stable so that the operating point doesn't shift is called as biasing. So, biasing and stabilization is an important concept in the working of BJT circuit or BJT amplifier, we can say. What is the need for biasing? First of all, we will see what is the need for biasing. What is the need for biasing? So, as already said, the BJT has to be forward biased in the input side and reverse biased in the output side so that it operates in active region properly. So, in order to do this, in order to perform this, we will go for applying external voltage, which is nothing but biasing the circuit. Appropriate DC supply we will be providing for the circuit. And we have also seen that the collector current IC, right, once it is fixed, IC VCE is called as operating point. So this operating point has to be in the center of the active region in the characteristics of common emitter configuration. So we should see that this operating point doesn't shift. The technique of biasing should also fulfill the stabilization concept. The particular biasing method which fulfills biasing as well as the stabilization is the best method. Now we will learn all various techniques in order to bias the circuit, BJT circuit, and we will try to come up with a biasing circuit which is most appropriate for all the applications. Means we have to learn biasing as well as stability factor, stabilization in a particular technique. So first we will take fixed bias. What is fixed bias? See, we know that among common emitter, common base, common collector, common emitter is the best configuration because it gives very good voltage gain, good current gain, okay, and as well as moderate or very good input resistance, high input resistance and low output resistance. These are the required design factors which a particular BJT amplifier needs, isn't it? So, we will see common emitter configuration with the fixed bias. So, this is the transistor. The position is such that you will have common emitter configuration from this. Okay. Now, we will use one power supply. How you have to understand the circuit, then you can remember it for long time. So, here we will apply one power supply, okay, battery. So here is a battery, we drop across this, which is going to bias this. Okay, so this is positive. So we have to check whether the given biasing is providing the basic necessity that input side is forward biased or not. Let us now check for that, right? So at the input side means this, we are actually going to give the input overall amplifier circuit. If I want to draw, nothing but I will connect the capacitance here. Okay, so we will have a AC supply here, V in, whichever we want to go amplify, right? And at the collector we are connecting the output. So hence this is the collector. From here we will take the output through the capacitance, so that we have the output across this, or we have a RL. Okay, so we are going to take the output across the collector. Now this is PN, so this is NPN, transistor NPN. So this is P side, right? So in order to forward bias, P side should be connected to P terminal, positive terminal of the battery. So let us see whether this is accomplished or not. So P side is being connected to, this is VCC. This means it is a power supply. Negative of this power supply will be connected to ground. That is not shown in the circuit generally, right? So P side is connected to P of the terminal. Obviously this is forward biased, right? So we have fulfilled one criteria, that is forward bias at the input side is done. Okay, we will now see whether output side or the collector emitter side is reverse biased or not. This is another point. So see here, this is what N, this is N, P, N. I have taken NPN transistor. So this is N, right? So N should be connected to P in order to make the reverse bias, correct? So this N is connected to P. This power supply battery is positive. Positive is connected to N. Hence it is reverse bias. So we have fulfilled the criteria that input side is forward bias, output side is reverse bias. So this is done. Biasing is accomplished. Okay, biasing is accomplished. So we see here, in order to do the analysis, we go for DC analysis generally. So DC analysis, in the sense we are not giving AC input. When AC input is not given, when this AC input is absent, capacitance offers very high reactance for this. So the capacitance acts as open circuit. Therefore, the capacitance are removed. So for DC analysis, we will remove the capacitances. We will not apply the AC input and capacitances are removed. Okay. Now this is called as DC circuit. DC conditions prevail over here. How the analysis goes on, what is that we need to find in any biasing circuit? Very simple friends. We need to find all the currents and we need to find the voltage at the output side. That's all. Currents means, see here, current which is flowing into the base. The moment power supply is applied, current starts to flow through this. Like this, current starts to flow into the base. I will call this as base current IB. This is called as base current IB. Okay. Now, once base current is set up, we have collector current, right? We know So writing KVL, VCC minus IVRB, there is a voltage across this VBE, we know that. So this is base, this is emitter. So here between this we have a voltage called as VBE plus minus, isn't it? Which is 0.7 or 0.6 volts for silicon transistor and 0.3 volts or 0.2 volts for germanium transistor. We know this, right? So this and then to ground. So writing KVL to the base circuit, we will get VCC equals IVRB plus, see, VCC equals IVRB, current IB is flowing, so hence it is IB over here, plus VBE, okay? Or you can also write it first step as VCC minus IVRB minus VBE is equal to 0. Then it comes to VCC equals IVRB plus VBE. So for any basic circuit, first you obtain IB, equation for IB, okay? So writing equation for IB, we have IB equals VCC minus VBE by RB, okay? VCC minus VBE by RB. This is the expression we get for base current IB, okay? Base current IB. Now you observe here, what is VCC? It's a constant, generally 15 volts, 12 volts we will be applying for the circuit. VB as already said 0.7 volts. RB is some resistance fixed value, the value which we have designed, right? So some fixed value, we will be having the value of RB. Therefore, since all these parameters are constant, IB is constant, and in order to, this is biasing is done, right? Next step is we need to find the stabilization factor or stability factor. In order to find the stability factor, we will differentiate this IB, okay? Therefore, dIB by dIC, differentiate with respect to IC in order to find the stability factor, okay? Yes. So dIB by dIC, differentiate this equation with respect to IC. So when I differentiate, what will I get here? Because this is constant, this is also constant, all the things are constant involved, hence dIB by dIC is 0. dIB by dIC is equal to 0. Now if we substitute this in the stability factor formula, we know the stability factor formula, general formula for stability factor. If we substitute this, what is that we will get? We will get, so general expression for stability factor, yes. General expression for stability factor, yes, is given by S is equal to 1 plus beta by 1 minus beta into dIB by dIC. Okay, so this is the general expression we get. Substitute this in this. Okay, what is that we will get? We will get stability factor for the fixed bias circuit. We will get the stability factor as 1 plus beta. What is the value of beta? What is the range of beta values? Beta values range from 20 to 300. It is very high. That is the reason why common emitter is very extensively used, or it's more popular, right? Now this high value of the stability factor, S is equal to 1 plus beta. This is not at all a desirable quality. Okay, so since the stability factor is very high, fixed bias is not a circuit which is going to provide good biasing and stabilization. This is the conclusion we draw. So since stabilization is very high, for proper operation of the amplifier circuit, the stability factor should be low. In the sense, we need not go for much stabilization for the circuit, right? It is already stabilized, means the operating point is already fixed, right? So KVL to collector circuit. Collector circuit. Okay. So see here, VCC equals IC. All the drops voltages you have to add. That is KVL. So VCC equals ICRC plus VCE. Okay, ICRC plus VCE. Fine. So from IB we already obtained IC. Okay. So we know that beta equals IC by IB. Therefore IC equals beta times IB. So beta IB we obtained, IC we obtained, and lastly we are left with VCE. Okay. So VCE we can obtain from this equation. VCE is equal to VCC minus ICRC. That's all. Okay. So for any biasing technique we need to find these things. Write KVL to the base circuit, obtain the expression for IB. From IB, beta times IB will give IC. And write KVL to the output circuit, you will get VCE. That's how. These are the things. And IC, VCE together. So this IC, VCE, they are called as operating point, Q point. Okay. So in order to find the stability factor, we have to differentiate the IB equation and substitute in stability factor formula, general formula I have written here. So this is how the biasing and stability factor are determined for fixed biasing. Okay, for fixed biasing. We will learn the other type of biasing. I have listed 5 different types of techniques for biasing and stabilization. We will learn other types of techniques in the subsequent lectures. Thank you for watching this video. If you like and if you feel that this video is useful, please subscribe, like and share the video. Thank you.